Here are some quick notes on the S process to accompany Chapter 7 of To Build a Star. Now, it might not seem clear right at this moment why S process nucleosynthesis is related to late-stage stellar evolution, which is the topic of Chapter 7, but if you don't already know the connection, just trust me that we'll get there. First, let me lay out the case for why neutron capture processes were first suspected to contribute to the chemical abundances in the universe. So the basic idea, or the signature that people saw, is, and this is basically how every process is identified. You look at abundance patterns and then you try to understand them. So people saw is if you look at the solar abundances, so you can determine these abundances of elements from meteoritic samples, from spectroscopy of the photosphere. You can then weight the abundances of these elements by the natural isotopic abundances. So now you have abundance versus the mass number. And now you see very striking patterns start to appear. You can then further go ahead and bend these by neutron number, and you can see some of the patterns are retained here and then give you a hint that these are maybe connected. Some of these are maybe connected to neutron numbers. The alpha elements and the iron peak, we'll talk about these more in some future quick notes on supernova nucleosynthesis and compact object nucleosynthesis. So just wait for those. But then we have these peaks that are labeled S and R, and as I'll show in a moment, these are connected to neutron magic numbers. So 50, 82, and 126. A magic number is basically a number of nucleons that, when a nucleus has that, it's more energetically bound than it otherwise would be, than you'd otherwise assume from, for instance, your liquid drop model picture that we talked about in an earlier quick notes. And so the idea then is when this pattern was first seen is that you must then have some astrophysical processes that there's a lot of neutron captures that are happening, and then because these magic numbers are more bound than neighboring nuclei, neutron captures would be very slow on these nuclei, the ones with neutron numbers 50, 82, 126, and so your abundances basically will pile up at these locations. It's kind of like having stop signs in the middle of the town, or traffic lights in the middle of your town. On average, more cars are going to be piled up at the traffic lights than anywhere else, and so you'd expect to get these abundance patterns. So just elaborating a little bit more on this, what we can do is we can take our abundance versus mass number plot. We can then kind of line it up roughly with increasing mass number on the nuclear chart, so sort of roughly with the n equals z slope. And then now let's imagine different neutron capture scenarios. So let's say we have one that proceeds mostly along the valley of stability on our nuclear chart. So in the background grayed out, you have the nuclear chart. Proton numbers vertical direction, neutron numbers horizontal direction. Each box is a given isotope of an element. The dark ones here, these are the stable nuclei, and then these bands are your magic numbers. So let's imagine you have a neutron capture and then it beta decays. And neutron capture, beta decay, and you march up stability. Well, then your traffic lights that you'd pile up at are going to be located at these magic neutron numbers, and then you can project onto mass number, and indeed, that's where you see a peak in the abundance pattern. As we'll get to in a future quick notes on compact object nucleosynthesis, if instead you had a process that was proceeding for very exotic nuclei, you'd hit your stoplights further away from stability. When the neutron flux dies down and the environment cools off, you'd beta decay back to stability, and you'd then get these peaks at slightly lower mass number. So that's your R process. So this S process must be slow relative to beta decay timescales. That's what the S stands for. And the R process must be rapid relative to beta decay timescales. That's where the R comes from. Okay. We can work out the rough time scale, how long does it take for a nucleus to capture a neutron. We don't need to dwell on this. We basically assume some number density. We assume some environment temperature, and these are going to come from astrophysical models, or as I'll show in a moment, you can actually kind of infer them from neutron capture cross-sections on Earth. But you go ahead and you do this, and you can pause the video and look at this later to see the math worked out. You basically, if you assume a given environment temperature and a given neutron density and take typical neutron capture cross-sections, you find that for a given nucleus, it'll take about a decade to capture a neutron. And so that's how slow is. If your beta decay half-life is less than a decade, then that is going to be faster than neutron captures. And so you're pretty much going to stay along the valley of beta stability, with a few exceptions of, relatively long-lived nuclei that are near stability. So then let's consider the reaction flow. And this will help us understand the abundance pattern that we get a little bit better. So again, we have our neutron environment with a relatively high neutron density, 10 to the 8 neutrons per centimeter cubed. And we can imagine we have nuclei kind of bathing in this environment. So then if we take a given isotope and we want to look at the change of the abundance of that isotope, so it's defined by a given number of protons and total number of nucleons, the rate of change is just going to be the production rate minus the destruction rate. And you don't need to understand this completely, just know that the production rate is obviously going to depend on the number density of neutrons, the number density of your parent nucleus that's undergoing a neutron capture to create the nucleus you care about, and the reaction rate for that neutron capture. And similarly, the destruction rate is going to depend on that neutron number density, the number of nuclei that you have that are going to be destroyed, and that destruction rate. And then this is just your beta decay rate and the number density of the nucleus you care about. As we said, this is a slow neutron capture process. So let's just assume the beta decays are very rapid, right? So we can just then ignore that. So that last term we're going to set to 0. We also can note that the way neutron capture cross-sections go, we mentioned in the cross-section quick notes, you have a 1/v dependence of your neutron capture cross-section. And so that sigma v there is going to basically be constant. And so we're just going to go ahead and instead of taking a thermal average, which is what the brackets represent here, we're just going to take your cross-section at a given environment energy, given by the temperature, and a velocity, given by the thermal velocity. So then our abundance change becomes simpler here. We still have production minus destruction, but we've popped out this product of the number density and the velocity of your neutrons. So that number density times the velocity, that's just a flux, right? And then if we integrate over that flux, then that gives us something we call the neutron exposure. We're often more interested in the neutron exposure than necessarily the details of the flux as a function of time, because as long as the flux is low enough so that you still have a slow neutron capture process, all you care about is, how many neutrons did you have a chance to capture over time, right? The integral is more important. So then we can basically then say, okay, what's the rate of change of our nucleus with respect to the neutron exposure? And we get that this abundance change is just the difference between your production minus your destruction. And again, we're just dealing with the cross sections and the number densities here. If we're going to reach an equilibrium situation, which will happen, eventually things will equilibrate, then what we find is that the production cross-section times the number density of the parent nucleus, that's equal to the destruction cross-section times the number density of the nucleus itself. And so this being constant here means that we can determine number densities of nuclei of isotopes isotopes along a given element. We can determine the ratio of those abundances just based on terrestrial neutron capture cross-sections, which is kind of amazing. And this is something that's known as the steady flow approximation. So the steady flow approximation, if we confront this with reality, we can take, again, the product of our cross-section times the number, and in this case, the abundance of a nucleus, plot that versus the mass number, and we see we do have these regions where that sigma n is roughly constant. We're cheating a little bit because this is a log scale, but it is roughly constant here. You get big drop-offs at the magic neutron numbers, which we might expect at a magic neutron number, your cross-section is going to be atypically low because magicity means sort of enhanced binding. But in any case, the steady flow approximation is pretty close to right. So how do we determine the deviation from the steady flow approximation? We can basically cross-check our S-process abundances that we predict with some cases where you can only produce an isotope from the S-process. So for instance, if you take tellurium 122, 123, 124, you cannot make these via rapid neutron capture, because if you made very exotic neutron-rich nuclei and let them beta decay back to stability, you are shielded by these stable isotopes. And so these ones here are only going to be made by the slow neutron capture process. So you can cross-check your S-process predictions here and then basically fine-tune things. And ultimately what we really do nowadays is we use a full astrophysical model calculation, right? So nowadays we know most of the neutron capture cross-sections pretty darn well for the stable isotopes. What we care about especially are nuclei that have a half-life similar to that neutron capture time. So, you know, on that order of the year, decade, around there. Half-life, then we care, because you could either beta decay or you could neutron capture. That's called a branch point. And this is going to alter your final abundance pattern for your S-process nucleosynthesis, but this also gives you a unique chance to have, basically, to constrain the astrophysical conditions. Because you have a neutron capture, which is temperature sensitive, competing with a beta decay, which mostly isn't, then this is going to be a probe of your environment temperature and also your neutron number density. So these branch points are special because they allow us to benchmark our astrophysics model calculations. So then on to the actual astrophysical environment itself, which connects finally to the content of Chapter 7, where we talk about asymptotic giant branch stars. So it turns out S-process neutrons, or rather S-process nucleosynthesis, comes from several different environments, and so you need different types of neutron fluxes. So there's basically the weak, main, and strong S-processes, and these occur in different locations. So your weak S-process, this is helium burning in massive stars, the cores of massive stars. And then the main and strong R processes, these are in asymptotic giant branch stars. And you're producing just sort of the heavier elements. What I want to focus on in particular here is the main S process, because this makes most of the S process elements, and it's particularly relevant to Chapter 7. So what we're doing here is we're zooming in on a very thin slice of the outer layer of an asymptotic giant branch star, and we're looking at something called a Kippenhahn diagram. So we have a radial coordinate, but in units of the mass versus time, and it's common that you're going to use different scales for parts of the Kippenhahn diagram here to see what's going on. So in this part of your asymptotic giant branch evolution, you have a carbon-oxygen core, a helium-burning shell, a basically inert, if you will, unreacting helium intershell, and then a hydrogen-burning shell. So you're building up this onion structure of the star. What can happen is eventually your hydrogen burning builds up enough extra helium that you can have a flash of helium. Okay, so you have a brief thermonuclear runaway, and that creates this convection zone here, and that is going to mix material, and it does that on the order of a century or so. So you're now mixing together parts of your hydrogen rich region and your helium rich region. And this can also then drive convection near the surface in something that's called a dredge up. That actually brings the elements that you make in the process I'm going to mention in a moment up to the surface of your star. But in any case, your helium burning shell, this is going to create carbon through the triple alpha process. You're going to make carbon that way. When you mix hydrogen, you mix protons down into the helium rich region, then your carbon-12 can undergo proton capture. That makes nitrogen-13. The nitrogen-13 beta decays to carbon-13, and you can build up a pocket of carbon-13. Now we care about that because carbon-13 burns helium very easily. Carbon-13 alpha N has a very large cross-section. And so you can produce a lot of neutrons, and you do produce a lot of neutrons over 100,000 years or so, and that is basically bathing heavier nuclei that are in your envelope from earlier nucleosynthesis generations, basically. You're bathing those heavy elements in neutrons, and that is then creating your neutron flux for the S process that we talked about in a moment. You can also, for the higher mass AGB stars, you can get hot enough during these flashes here to burn neon, and you do neon-22 alpha N. And so for nuclear astrophysics, carbon-13 alpha N and neon-22 alpha N are extremely important reactions because these create the neutron flux for your S process nucleosynthesis. And they're so important that they're still being measured and studied today. So even though people have been measuring carbon-13 and neon-22 alpha N for decades, we need to know these cross-sections to very high precision if we want to accurately predict the astrophysical conditions for the S process and the abundances of the S process elements. And that is it for these quick notes on the S process.